Hi there, I'm Stefan, developer advocate for Zillits in the Bay Area, and today we're joined by Jay Bjorn, one of our solutions architects. We'll be chatting about Zillits Cloud and vector databases more generally, and Jay will help us architect some solutions to frequently asked questions. So we'll cover things like how to choose an indexing algorithm, the recall latency trade-off, whether long context LLMs make vector DBs obsolete, use cases of vector databases outside of RAG, and several other really interesting topics. So stick around and discover whether I can fool facial recognition with a fake moustache.
A question that comes up a lot is, how do I choose like an indexing algorithm for my vector database? So I know like in Milvus, you have a lot of choices.
Yeah.
Is that the same in Zillits Cloud?
Well, no, I think, if you're asking a question about whether or not you should pick one index algorithm or another, I think you probably might not be a good candidate for a managed service like Zillits Cloud. A lot of the managed service products kind of make these decisions for you. Like, it's not really something that, most end users find themselves concerned with. Most of them end up making a predefined set of trade-offs, right? So they'll pick one index algorithm type, and they may make some modifications to it to fit, the hardware that they're running it on, or, any other parameters that they're trying to tune. But Zillits approaches this problem a little bit differently. We feel that there's a lot of use cases where you might want to tune whether, I really care about recall accuracy in this particular scenario versus I really care about query latency in this scenario. Right. And I'm willing to take a hit in either direction. So, Zillits has a proprietary index engine called Cardinal, which we've rolled, and it allows you to essentially tune this on the fly, right, on a per query basis. So if, for example, you want to send one query, and you basically want to tell Zillits, hey, look, I really, really want you to return this as fast as possible, right? And I'm willing to take a hit on recall accuracy. You can tell us to do that. And there's a parameter called levels that allows you to do that in Zillits Cloud. It's an integer between 1 and 10. And
do I have to defeat a boss to get to the next level?
No, you don't. You can send it however you want, and however many times you want, and however many which ways you need to.
That's really
based on your use case. So yeah, it's pretty flexible in that nature.
Yeah. Awesome. Yeah. So I like it how like really sort of made it a simple choice. You've sort of like quantified like the main trade-off. But I'm sort of like curious, like, why does this trade-off exist? Like, why can't we have both low latency and high recall?
Yeah, it's a really good question. I think a lot of folks who come from any other type of database kind of struggle with this because, all the databases that we've come from, NoSQL, SQL, they're essentially deterministic databases, right? So you ask them to give me something and it's a binary outcome. It's either there or it's not, right? Versus with vector databases, it's a lot trickier, where you're tasking the vector database to do a lot of geometric measurements, right, in multidimensional space. So there's no real good way to brute force your way through this problem in most use cases, since the amount of measurements that you need to take to approximate how many neighbors are nearest the point that I'm trying to measure, right? So in a semantic context, it would mean I have a query, give me all the chunks of text that are closest to this query, right? Doing all of those geometric measurements for every single vector in 1,536 dimensions is a very taxing operation. So the way that this is overcome in modern vector databases is we don't use known nearest neighbor, we use approximate nearest neighbor.
Got it.
And that essentially creates this scenario where it is not fully deterministic. So you may get most of the neighbors most of the time, right? Which is why the index algorithm that you pick is really important because some of them optimize more for, I want to optimize for getting as many of the neighbors as possible, but that is an inherently more taxing operation versus there are other algorithms that sacrifice that for the sake of query latency.
What's sort of like a typical recall that we could expect? Is it like, okay, it's approximate nearest neighbors, but I only get like 10%? What would be a typical
Yeah, so typically you want to shoot for higher than 85%. Anything lower than that, you're missing a lot of neighbors. And it most of the time you can get pretty close to 95%.
Yep.
And you can still hit P95s that are pretty respectable in like the sub 1,000 millisecond range. Obviously, there's a lot of other factors that go into an ANN search. What's the total size of the vector space? How many dimensions are you searching across? Are you doing any kind of metadata filtering after the fact? These all factor into the total latency that you want to try to hit, and it's going to depend on the use case that you have, right? So, for example, if your use case is user-facing and your users are waiting for you to respond, you might take a hit, in recall accuracy. But to answer your question, you generally want to go between 90 and 99% is kind of where you want to sit for most use cases. Anything below 85 to 80 is it becomes a little questionable, whether or not you want to use this.
You mentioned that to brute force your way out of an exact nearest neighbor search is not feasible once you reach a certain scale.
Right.
So just so we have a sense of the scales, when would you sort of say someone should transition from just a naive brute force search to a one of these special algorithms?
It's a good question. I think it also depends on how much money you have to spend. With enough hardware, you could brute force your way out of a lot of these problems, but it just becomes economically infeasible for a lot of use cases. I would say it is highly dependent on the number of dimensions that you're trying to measure. Once you're in the millions and tens of millions of vectors and you're working with any dimensionality higher than even 384, it ends up being a quite a taxing process right now. So that's why we have a lot of these modern approximate nearest neighbor type algorithms that allow us to perform this operation with minimal cost to the recall accuracy. And it still gets us pretty much all the way there, but it gets us an order of magnitude improvement in the query latency, which enables a lot of these use cases that we're seeing today, like recommendation engines, RAG pipelines, fraud detection, and things like that.
I know when people are talking about size, they're like, oh, it's 10 Olympic swimming pools or 5 football stadiums to sort of make it really sort of relatable. So how would you sort of put it for, say 1 million, what can you do with 1 million vectors with sort of a standard model? Is that all of a company's internal data? Is it a whole website, multiple websites?
It's a good question. And it's a loaded question as well, because there are a lot of variables that we're trying to measure. I would say, the first thing that you want to measure is the dimensionality of your vectors. And most of the time that's set by the embedding model that you're using, right? So the embedding model is this very expensive pre-trained transformer that allows you to essentially take a piece of text and place it in its universe of vector space, right? And within that universe, there are going to be coordinates that come out. And then, if you give it, 100 words, it'll give you some fixed length of vectors in vector space and location in that universe where it thinks it makes sense to place it. Different embedding models have different dimension lengths. So it's not a one-to-one comparison, right? So the other lever you get to pull is how large are these pieces of text that you're feeding into the embedding model, right? So if you have a very long PDF document with hundreds of thousands of words in it, you're probably not going to want to feed that whole thing and create a single embedding, right? You're probably, because parts of that document are going to have different semantic contexts. So you're going to want to separate that document into sections. We call them chunks, but you essentially want to separate the document into manageable pieces that make sense from a recall standpoint. So if you're recalling the front of the top of the document, right, versus the bottom of the document, those might be completely different locations in vector space. Yeah. So to fully answer your question is a little tricky because there's a lot of these variables.
So, what if we were to say, take a really sort of out of the box, sort of general purpose ones, dimensionality, say 384.
Yep.
you're sort of representing your numbers in 16 bits. So yeah, is there some sort of like a sense of like what can you do with that?
Yeah, I think where semantic search gets really powerful is being able to search across a vast array of documents, right? So, I would say, if you have more than, 1,000 documents and they're all 5 to 10 pages long of double spaced 12-point font, yeah, that's going to be considerable. The operation to search across that from a no nearest neighbor perspective is going to start breaking down. Unless you have crazy amounts of hardware you want to throw at it, then it's probably okay. Yeah. But you end up with these diminishing returns after a certain point, and most of the time it makes sense to start exploring a lot of these approximate nearest neighbor, non-deterministic kind of paths to perform this operation.
Got it. And one thing that you mentioned, I thought was really interesting. You said the chunking strategy you use can really affect the size, like the number of vectors, the size of your vector database, and therefore the hardware requirements. So I wanted to ask you a bit more about that. So I guess there's sort of like a trade-off between, if you have like a really small chunk, then it's maybe like it doesn't encapsulate like say like a paragraph is sort of one of the smallest semantic units. Whereas if it's too large, maybe the model can't actually input that many an input of that size, or maybe it just sort of contains too much information within those limited dimensions you have.
Sure.
So what would your advice be for chunking strategy? And like maybe an extreme end of things. Now that we have really long context window large language models, do we even need a vector database? Like why can't we just stuff our whole document or 1,000 documents into the context of this LLM?
Yeah, that's a really good question. I think, now that we have these incredibly large context windows, this is now up for debate. Even just like a year ago when the windows were much smaller, this was a lot easier question to answer, right? I think now it's, a bit more ambiguous. What I will say though is, despite that the windows are still large, it is possible for the LLM to either underweight or overweight parts of the window. Generally the beginning and the end are overweighted. And especially if you have conflicting context in the window itself, the LLM might get confused and not answer your question correctly. So the size of your chunk is actually still important. There's a lot of low-hanging fruit things that you can do. Like, for example, like don't truncate mid-word, don't truncate mid-sentence, right? Infer the structure of your document and make sure that right. Like you don't want to give the LLM like a half of a word, right? So those are probably the first things, that kind of the low hanging fruit that you should at least shoot for. And then there's a lot. This gets kind of crazy. You can kind of get a little crazy with this. Like there are folks that manually go and clean their data perfectly so that all the chunks are of the appropriate size. They're actually, context aware of each chunk so that they're not separated, meaning that, for example, like they won't be of fixed sizes, right? So if a paragraph is maybe a little bit longer than what an ideally sized chunk should be, it would still keep that paragraph together because it's all still semantically relevant, and you want to place that whole paragraph in vector space. Obviously, this is a very onerous task to do if you have terabytes and terabytes of data that you want to be able to embed. So again, it's going back to what we were saying earlier about no nearest neighbor versus approximate nearest neighbor. There's ways to kind of, get an order of magnitude improvement in this kind of chunking strategy, while also kind of maintaining as much of the semantic accuracy as possible. There are tools like Unstructured. There are frameworks like LangChain and Llama Index that kind of help you kind of infer and understand and kind of chunk these documents in a much more automated way than you kind of going in and either, picking a fixed length or going in there manually. Obviously, there's things like Mechanical Turk that you can use as well. If you want more of a human element to look at this. You can also use LLMs as well, as long as you're willing to pay.
Yeah.
for the tokens. That's also another very popular way that folks do this as well. So
sorry to cut you off there, but a thought just popped into my head. So you mentioned like paying for the tokens.
yeah.
So suppose I like stuff all of like my 1,000 documents into the context window. Does that mean that my sort of my inference, my LLM is going to be, does that sort of play into the cost of that?
Yeah, it does. It's also an important parameter to measure as well. I think right now the cost of inference, I think, is still relatively high. It'll be interesting to see what happens, as, the chip manufacturers kind of bring the cost of inference down.
Yeah.
Maybe in the future, this may matter a lot less, right? But right now, it is something to measure as a cost.
Yeah.
It will generally dwarf what you're paying for anything else, in terms of RAG pipeline. So you want to be as optimized as possible by feeding only what you need to into the window, not just for economic reasons, but also just for, to mitigate the probability of hallucinations.
Yep. Yeah, totally. So one thing that sort of seems like sort of very apparent to me is like vector search is a very cheap operation relative to large language model inference. So, if like a search over, say, terabytes of text or images, videos, I get that back within 10 milliseconds. That seems like a pretty good deal. So something sort of like very, very inexpensive way to give a large language model an external memory.
Yeah, that's right. I mean, that was really the first kind of killer app for a lot of these vector database solutions was essentially to provide the LLM a way to answer questions about data that it wasn't originally pre-trained on, right?
Yeah.
And this is a very common use case for enterprises or just, anyone in general who has private data that was not originally accessible to the LLM. There's a very seamless way to, search across all of that data in a semantic context and then feed it into an LLM so that the LLM is able to answer specific questions about your own data. So, yes, it is a relatively inexpensive operation, relative to inference.
Yeah. So Jay, I know I can use vector databases for RAG, for agents. Is that like the only thing they're good for?
Yeah, I mean, obviously, RAG has been the killer app for vector databases thus far, at least for the last 18 months or so. But when you think about them, they're essentially just measuring instruments, right?
Yeah.
That's what a vector database does. So it doesn't have to be just for text. There are a lot of image embedding models now. There are audio embedding models as well. And there's a lot of interesting things that you can do with them.
So, are we just talking like RAG over images here?
No, not really. I mean, there's like, I'll give you a couple, more commercial examples. There are companies that, are interested in doing image similarity search, not text similarity search. So right now we've been talking about text similarity search, where if you give it an image, it will also place the image in vector space, right? The embedding model doesn't know that it's an image. It's just bits, right?
Yeah.
So it'll place that same image in vector space. And then if you give it another image and ask it, hey, how similar is this image to the other image that I just showed you, right?
Yeah.
It'll be able to tell you with, it's exactly this far apart, right? In its, in its vector space. So this is particularly useful for, areas where the images are very similar, but they may be slightly different from like, oh, it's an off angle, or the lighting is slightly different, or areas where a human would be able to immediately pick up is like, oh, that's the same person, or that's the same plant, right?
Yeah. So you're talking about maybe sort of like a data deduplication or like a record linkage type scenario.
Those are very common use cases. A little more high stakes use cases than that would certainly be around like fraud detection, right? So making sure that, like for example, the modern kind of KYC type solutions that are out there right now, like require you to take kind of a photo of your face and then kind of a photo of the sides of your face. And this is really helpful for folks who run, fintech platforms where they provide some kind of incentive to come onto the platform. Let's say if you come onto the platform, I'll give you, $10 or whatever it is. A lot of folks like to game the system by creating multiple accounts and collecting that incentive multiple times. So it allows companies like that to say, have I seen this face before? And you'll feed it through all the faces that you've seen so far. And with faces, sometimes it's a little tricky. They'll like wear disguises, or they'll change their hair, or they'll wear glasses, or they'll grow out their facial hair, whatever the case is. But imaging embedding models are still really good at picking up things that you can't change, right? So like the eye structure and like the pixels that are not so easy to change from a cosmetic standpoint. And they're able to pick those up and say exactly how similar is this photo, and then your engine will have to decide where the threshold sits for, maybe that gets escalated up to an actual person to review. And this is a really common use case that we're seeing for image similarity.
Got it. So you're saying that when I try and get back into the casino, they're gonna like I can't just wear like a fake mustache.
You are a unfortunately a known card counter, Stefan. So yeah, it's unfortunately not gonna be able to play anymore. You can play every other game though, okay?
So any other like interesting use cases?
There's with audio embeddings, this is also really interesting as well. So for digital rights management, there's a lot of work being done right now around being able to detect whether my copyrighted audio is being shown or is being uploaded to other areas. So before it was very tricky to know, is this part of the song the same as this part of the song, right? Like you can see if the bits are identical, but if it's say for example recorded on some other device, or somebody is singing it, right, or someone's doing a cover, right? So
you're talking about like automated copyright.
That's right.
Detection or enforcement.
It's digital rights management, right?
And so that's sort of like, I guess that's sort of like a similar thing to this image record linkage, perhaps.
Exactly. Yeah. Fundamentally what vector databases are really good at is saying like, how far away is this point from this point, right? And us humans, we live in 3 dimensions, so it's very difficult for us to conceptualize. But a lot of these embedding models have thousands.
We live in 4 dimensions.
Yeah. Well, it depends who you ask. But most people think XYZ plane, right? So if you think of 3 dimensions, you're able to measure the distance between 2 points in that universe. But these embedding models have hundreds or thousands of these dimensions, so it gets quite difficult for to grasp your mind about how many planes that this data is being sliced against. But what that ends up doing is it allows us to see similarity that humans might miss because it's being sliced into so many different dimensions. And obviously, at the bleeding edge of research in this field, we're starting to see even more advancements, and we may be able to compress the amount of dimensions that we might need and still get a similar result. So there's a lot of really exciting work that's being done, and I think vector databases will continue to be an important tool, not just for commercial applications, but also in academia, in governments, in a lot of other areas where you're going to need to measure distances very quickly, especially as the cost of inference comes down, and then especially as these models become more advanced and more intelligent.
I'm just imagine I'm like a dedicated student of vector databases, and I want to partake in this exciting universe. How do I get started with Zillits?
Yeah, sure. So you can go to Zillits.com and sign up for an account. You'll get some credits dropped in there as well. There's a lot of resources on Zillits.com as well. We have notebooks that you can look at for various use cases. Obviously, the Milvus open source community is a really good place as well. Our documentation is quite extensive for a lot of use cases as well. Obviously, the solutions architect team here at Zillits is always here to help. There's a wealth of resources out there. This podcast included. Subscribe.
Make sure you like and subscribe.
Thanks for joining us. Hopefully you got some useful pointers on how to use Zillits Cloud more effectively. If you want to find Jay, it's between I and K. But if you're actually looking for our solutions architect, Jay can be reached via his LinkedIn. See the video description below.